For the longest time, electricity and magnetism seemed like they were from two completely different worlds. One gives us light, the other points our compasses north. But it turns out they're really just two sides of the same coin, linked by this incredible, invisible connection that basically powers our entire world. So how in the world can a tiny moving charge create a whole magnetic field? Well, let's dive in. That probably sounds like a pretty weird question, right? I mean, on one hand, you have this massive, chaotic blast of electricity in the sky, and on the other, a quiet little magnet stuck to your fridge. But believe it or not, the link between them literally changed the world. And the best part? The discovery all started by accident. So let's meet the guy at the center of this story, Hans Christian Ørsted. Picture this, it's 1820. He's in the middle of a lecture, and he's got a wire with an electric current running near a compass. And he notices something absolutely wild. Every time he switched on the power, the compass needle would twitch and move. Just like that, he'd accidentally stumbled upon the very first real piece of evidence that electricity and magnetism were connected. And you really have to understand what a huge deal this was. Before 1820, these two forces were in totally separate worlds, scientifically speaking. You'd find them in different textbooks. Ørsted's simple observation kicked off this firestorm of research and experimentation that lasted for decades, leading all the way to James Maxwell, who finally unified them completely into what we now just call electromagnetism. So, what was the big takeaway from his experiment? The absolute key is this. It's not just about charge. It's about moving charge. An electric current, right? That's just a bunch of charges flowing together. And it's that motion, that flow, that generates a magnetic field all around it. That was the game-changing idea. Okay, so we've got it. Moving charges create magnetic fields. Simple enough. But what happens if you flip that around? What if a moving charge flies into a magnetic field that's already there? Well, it feels a force, for sure. But, and this is a big but, it's a really, really strange kind of force. And here it is, the famous Lorentz force equation. This equation tells you the whole story. The first part, the electric field part, is pretty straightforward. But check out that second half, the magnetic part. That's where things get interesting. See, the force depends on its velocity. And that little x symbol, that's a cross product. All it means is that the force pushes in a direction that's perpendicular at a right angle to both where the charge is going and the magnetic field itself. It's this one little detail that's responsible for all the cool stuff we're about to see. Let's put this side by side with the good old electric force. An electric field is simple, right? It just pushes or pulls a charge straight, making it go faster or slower. But a magnetic field is totally different. First off, it does nothing to a charge that's just sitting there. It has to be moving. And second, and this is the absolute key, it only ever pushes sideways. Now, just let that sink in for a minute. A force that can't actually do any work in the physics sense, it can't make something speed up, and it can't make it slow down. Why? Because the push is always sideways. All it can do is change the particle's direction. It's purely a turning force. A great analogy is a ball on a string. The string keeps it going in a circle, but it doesn't make the ball spin any faster or slower. And here's what that looks like in practice. It's pretty cool. If you shoot a charged particle into a uniform magnetic field, that constant sideways push just bends its path into a perfect circle. It's trapped. It can't speed up, it can't slow down, it just goes round and round and round. And this little dance is the secret behind some seriously heavy-duty tech, like particle accelerators, and even how old-school CRT televisions used to work. All right, let's recap. Moving charges make fields. Fields turn moving charges. Got it? But how can we actually, calculate this stuff? How do we predict just how strong a field is going to be, or which way it's going to point? For that, we're going to need a couple of new tools for our physics toolkit. Now, for electric fields, we've got Coulomb's law, which is nice and simple. For magnetism, well, things get a little messier with something called the Biot-Savart law. Just look at the differences here. The source isn't just a point, it's a little piece of wire with a current, so it has direction, and the field it creates points sideways, perpendicular to that wire. It's just fundamentally a more three-dimensional kind of problem. And this is where another giant of physics comes in, André-Marie Ampere. He saw what Ørsted had found and just went for it. He did tons and tons of experiments to really nail down the math behind this new force. And in the process, he gave us a much cooler way to solve these problems. He came up with Ampere's law, and honestly, it's an incredible shortcut. Instead of doing some crazy calculus adding up every little tiny bit of a wire, Ampere's law says, hey, just draw an imaginary loop around the wire. The magnetic field all the way around that loop is directly tied to the current punching through it. When you have a nice symmetric setup like a long straight wire, this makes things so much easier. Okay, straight wires are cool and all, but what happens when you take that wire and you bend it into a loop? This right here is where things get really interesting. This is the aha moment that honestly powers pretty much everything we use. So check this out. We've got a rectangular loop of wire sitting in a magnetic field. Now, based on what we know, the force on one side pushes in and the force on the other side pulls out. They're perfectly balanced, equal and opposite, so the net force is zero. The loop isn't going to go flying off in any direction. So nothing happens, right? It just sits there? Well, not so fast. Look a little closer. Yeah, the net force is zero. But the key is that those forces aren't pushing along the exact same line. If you look at it from the top, you see what's really going on. You've got a push on one side and a pull on the other. And what does that create? A twist, a torque. The loop doesn't get shoved, but man does it want to spin. And that simple twist, that is the secret sauce behind every single electric motor in the world. Does this have a name for this twisting tendency, of course? It's called the magnetic dipole moment. But all that really means is that a loop of current basically is a tiny magnet. Think of it like a little compass needle. It's got a north pole and a south pole. And if you put it in another magnetic field, it's going to try its best to line itself up. Simple as that. So this simple little twist on a loop of wire, it's not just some neat physics trick. It is an absolute powerhouse. It's the foundation for so much of the technology we rely on every single day. I mean, think about it. You stack a whole bunch of these loops together, you get a solenoid. That's how you make the super strong, uniform magnetic fields for things like MRI machines. You figure out a way to let that coil just keep on spinning. Bam! You've just invented the electric motor, the thing that runs your electric car, your blender, pretty much everything. And what if you carefully measure how much it twists? Well, now you've got a way to measure electric current itself, a galvanometer. So how does that last one work? It's actually pretty clever. You send current into a coil, right? The magnetic field tries to twist it, but you attach a little spring that twists back in the other direction. So the coil turns just until the magnetic twist is perfectly balanced by the spring's pushback. Then you just stick a pointer on it, and the more it deflects, the more current you've got. It's so simple, but it's absolutely brilliant. And all this led Ampere to this huge, really bold idea. He thought, okay, wait a second. If these current loops act exactly like magnets, what if all magnets are just made of tiny little current loops? He proposed that even a plain old bar magnet doesn't have some special magnetic stuff in it. It's just the combined effect of zillions of microscopic circulating currents. And just like that, poof! The two forces that people had seen as totally separate for thousands of years were suddenly revealed to be one and the same. It wasn't electricity and magnetism anymore. It was electromagnetism, a single, beautiful, unified force where each one can create the other. Which brings us to one last mind-bending question. Because here's the thing, Ampere was basically right. So, if there aren't little wires and batteries inside your refrigerator magnet, what in the world is moving? What's the tiny circulating current that's making it a magnet? Well, the answer to that question takes us deep, deep into the weird world of quantum mechanics and a fundamental property of electrons called spin.